All right, so when we're talking about temperature scales, there are three main temperature scales, right? You see these in your book. We have Celsius, Fahrenheit, and Kelvin. Now, the biggest difference between them is where and how we keep the scales separate, is where we identify boiling of water, freezing of water. Those are the main ways that we keep things together when we're looking at various scales. Because the scales were actually made for really different purposes. Celsius is actually based on water. 70-something% of the planet is water, 70-something% of you is water. Celsius just seemed like a good choice for making it based on water. So it boils, the boiling point for Celsius is what? 100 degrees. All right, good. And then what is the freezing point?
0.
Good. The freezing point is 0 degrees. This also makes this one of the easiest possible scales that you can have, right? This makes it very, very easy to use. I'm going to erase this section just for a second. We'll come back. 23 and 20, I'll remember. All right. And then the last thing is, we'll come back for this one. So it boils at 100 and it freezes at 0 degrees. So this one is based on the water. This is based on water. Who can guess what Fahrenheit is based on? Remember, people are inherently selfish. It's based on people. So this is supposed to be based on the human body. Now, there are some legends about this, including the fact that they didn't want to do experiments on humans to make the Fahrenheit scale, and so that instead they used them on, they used pigs, which have very similar body internal structures to humans. It's true, you can get like a pig heart implanted instead of a human heart if you need a heart transplant. Also, you can do cow hearts, although they're very, very large. You can run your whole hand through the valves. This is not the point. So, one legend is that they actually were using pigs, and that's why the Fahrenheit scale doesn't work out exactly even the way that it's supposed to. But however it worked out, it was supposed to be that 100 degrees was going to be the average body temperature on the Fahrenheit scale. Okay? And, oops. That didn't work out. What is the average body temperature?
98.6.
Yeah, like 98.6 degrees Fahrenheit is about average body temperature. Who knows what boiling is?
212.
212 degrees Fahrenheit is boiling. Okay? And what is freezing?
32.
32. Okay. Has anybody ever found that it is particularly annoying trying to figure out how freezing something really is when it's 9 degrees? Right? If it's 9 degrees Fahrenheit, that's a pretty difficult thing to sort of, how much colder than freezing is it really? Right? So because our scales are so warped here, right, that doesn't make a lot of sense. All right. And this is where Kelvin comes in. So Kelvin bases its scale, because both of these scales have negative numbers on them. All right? Kelvin bases its scale on the idea that there are no negative numbers. That absolute 0 is the place where all motion supposedly is going to stop. Okay? Physics can fight about that a lot. There's a good video for that up on the website that you can check out. But absolute 0 is where all motion is going to come very close to stopped, if not stopped. So freezing for Kelvin, does anybody know?
0.
Oh, except for no.
Freezing?
The freezing point of water is 273 Kelvin. The boiling point of water on the Kelvin scale, and you'll notice there's no degree markers here, okay? Because there's no negative numbers, we don't have to have degrees of anything, all right? So it's 373 Kelvin. On which two scales are the increments of temperature change the same? No.
Celsius and Kelvin.
Celsius and Kelvin. The difference between freezing and boiling of water on each scale is only 1 degree. Does everybody see that? So there's a 100-degree difference here and a 100-degree difference here, okay, between freezing and boiling. So Kelvin is set up so that there are no negative numbers, but each increment on the Kelvin scale is the same as if it was on the Celsius scale, which is why SI units, the System International, the standard science units for temperature, can be either Celsius or Kelvin. In our classroom setting, the standard SI unit is going to be Celsius. But if you were working in an extreme physics lab where they did a lot of stuff, where they were freezing things at a very low temperature, or if you were a scientist who was working on space and you needed high temperatures for rockets and high temperature or low temperatures for the sun and for the vacuum of space, you would definitely be using a Kelvin scale. And both of them would be acceptable, and the increments of change would be the same on both, so it wouldn't screw anybody up. Does that make sense to everyone? All right? Yes?
So you just add 273?
Yes.
If the increments of change are the same, then how is Kelvin different from Celsius?
Kelvin is different from Celsius because the absolute zero, the lowest possible temperature that we think could possibly exist for Celsius degrees is negative 273 degrees Celsius. But the lowest possible temperature that we think exists on Kelvin is absolute zero. It's just 0 Kelvin. And then it's like 400 and something, negative 400 and something for this one. And you can look that up in the textbook. I'm sorry, I don't know it off the top of my head. For Fahrenheit. So if I had something that was 0 degrees Celsius, 0 degrees Fahrenheit, and 0 degrees Kelvin, which one is the coldest? Kelvin. Okay, by a lot, right? 0 Kelvin is by far the coldest. What's the next coldest one that's 0 degrees?
Celsius. They're equal.
Fahrenheit. Remember, the freezing point of water on Fahrenheit is at 32. So 0 is going to be even colder than the freezing point of water, where 0 on the Celsius scale is the freezing point of water. Does that make sense to everybody? Okay, so you just try to keep those scales level in your minds.